Hello, welcome to this talk on the topic of the Bruling sieve and a proof of concept of a ubiquitous method for the fast factorization of semiprimes. My name is John Bruling, and on this agenda we will talk about what is the Bruling sieve, the short history behind it, an example of the sieve, how it relates to the structuring of all prime numbers, how that information was used to define a fast semiprime factorization algorithm, and a proof of concept example of this algorithm. The Bruling sieve is an assumed previously unknown mathematical conjecture applicable to all primes greater than 5, and is as follows. Any prime number applied a mod function with a value of 30 will result in one of 8 values between 1 and 30. These values are 1, 7, 11, 13, 17, 19, 23, or 29. Greater than 5 that does not yield one of these values listed cannot possibly be prime. This removes 4 of the 12 possible values for calculating the primality of any odd prime potential number, meaning if you apply the mod 30 and you receive 3, 9, 21, or 27, then it cannot possibly be prime. The omitted values 2, 3, and 5 are technically prime, but only appear once as mod values for the corresponding integers 2, 3, and 5. While the others are repeatedly called. These 3 values are totally exclusive to themselves, while all of the other mod values are shared amongst all the other primes, and it was with this in mind that 8 was decided upon as the number of mod values given, despite the minor technicalities. It's assumed previously unknown because it's a definitive quality of all primes greater than 5, besides their characteristics of non-divisibility. There are similar tools for ordering out primes, such as factor wheel, but no instances of a specific usage of a mod 30 function for filtering out all odd potential prime candidates that I could find. It all began, essentially, with my desire to draw a fractal with a turtle crate. As you can see here, I had only ever generated it on Android and in fractal generators, and I wanted to do something better. Now, I won't go into the history of this particular fractal, but it is rather interesting. I became distracted initially because there were no good spiral formulas. I decided to set about writing spirals for turtle graphics in Rust, and I accomplished this after doing a bit of research. In that research, I became reacquainted with the Ulam square spiral, which is shown here. And plotting the primes on this spiral reveals some interesting patterning, albeit fairly chaotic. And so I decided to plot the primes on an Archimedean spiral, which is one of the ones that I had figured out how to draw. Essentially, it's a circle where every little line segment is just a little bit longer than the previous one, and so it illustrates a type of increasing relative velocity, which is why the spaces between each ring are concentric, essentially. The loop of each spiral is 360 line segments. To draw a circle in turtle graphics, you might draw one line forward and then turn 1 degree, and then repeat, and after 360 times you will be back where you started. And that was the idea. The image that it produced was quite interesting. All of the primes, as you can see plotted in black, line up. In this case, in 96 specific rows. There are other images out there that are similar to this, but there's always chaos and primes peppered throughout. This is all of them in lines without exception. And so I thought that was rather interesting and required a little bit more research. Just looking at the image, we can see that it appears to have some kind of a patterning going on that may even be symmetrical. And so I set out to grab the numbers that show up in each of these lines. And it turns out that they are 12 repetitions of 8 paths across 30 line segments. Paths, the term chosen here because they go in straight lines. The repetitions defined as the results of a mod 30 function applied to all the contained primes in the given path. Essentially all of them along the line will result from a mod 30 function in either 1, 7, 11, 13, 17, 19, 23, or 29. The image indicates that it holds true from at least 0 to about 640,000-ish. Now, to further test this conjecture, they've simply applied the sieve, as it is, as a match filter on the prime check used in the Turtle program. Basically, any number that results from a mod 30 in 3, 9, 21, or 27 is completely skipped and not checked for primality at all. All of the rest of the primes are counted as they're found, and this test holds true up to the millionth prime, which was the highest that I ran it at, which is 15,485,863. The code for this is contained here at the archive at this link, and you're encouraged to try it out. Here's the same circular image plotted out in a horizontal fashion where the numbers count from 0 down 1, 2, 3, 4, 5, 6, 7 to 29, and then come back up 30 down to 59, up to 60, down to 89, up to 90, as you can see. And it goes along to the right to 300,000. We can immediately see that all of the prime numbers here essentially are one of these 8 base primes, as I've attempted to call them, plus some increment of 30, or 30 times an amount, or 30 to some power. It's unknown exactly, but they are increments of 30. This has interesting ramifications when it comes to multiplying prime numbers, because essentially we're just multiplying the 2 base primes and then adding the product of those 2 increments of 30 that either might have. For all of the base primes, there are 36 possible products. These products themselves relate to each other in functions of mod 30 and are applied by the color scheme, as you can see. This means that if we subtract by trial these 36 products and apply the mod 30 to the remaining semi-prime value and get a 0, then we can deduce a particular set of prime numbers that would have multiplied to give that number. And because of their relationship, it is sufficient to simply apply the mod 30 and get one of the 8 base primes. Here are some examples, and you can cross-check these if you want. The 2 prime numbers, 2,986,859 times 2,109,311 equals 6,300,214,544,149. That number, mod 30, equals 19, which equals the mod 19 group. And if we apply the mod 30 function to the factors, which we know, we can see that 29 and 11 both appear. Same for the number below. The same for these 2 numbers as well. And the same for these 2 as well. It was decided that a proof of concept of this was needed. And so, firstly, the numbers contained within the given mod path group were collected into files from 0 to 3 million. This was an arbitrary number chosen simply because it was large, but not too large. The large file sizes and specific programming method was limiting, so it is actually 4 proof of concept programs where each one handles 2 of the 8 total path groups. We begin by applying the mod 30 function to the semi-prime and match the output to the path pairing groups. We then get the square root of the semi-prime. We get the first prime on the first list that is just above our square root, and then the first one below it. In this case, L up and L down, meaning left. Then we'll get the first prime on the second list just above the square root, and the first one below, R up and R down. Then we start cross-multiplying L up and R down. If product is greater than the semi-prime, then we lower L down to the next value, and if it's less than the semi-prime, we'll raise R up to the next value and cross-check through the entire list. If the product equals the semi-prime, then we are done. We found the solution. and the program exits. If the values in the list are exhausted one direction or another, then it moves to cross-multiplying the R up and L down values in the same fashion. If the values exhaust again, then it moves to the next pairing. The proof of concept is designed to explicitly show that only one of the 8 pair groups is ever searched, all of the other 7 are completely skipped, and the semi-prime factors are contained within one of the pairings within the selected pair group. Implications. Well, this is a big part of public key cryptography, particularly with RSA, with Diffie-Hellman key exchange methods. Here's RSA 1024, 309 digit that has yet to be factored. However, we can see from the mod 30 result it is 13, and that the factors would be contained within one of these 4 path groups. We can see very clearly an RSA 240, which was factored in 2019. Applying the mod 30 function to it gives 19, and the mod 19 path group, applying the mod 30 function to either of those numbers, both results in 17, which is contained within this mod pair group. RSA 250, factored in 2020, mod 30 equals 7, which equals the mod 7 group, and applying that to either factor gives 17 and 11, which also is contained here. These numbers were taken from the RSA numbers on Wikipedia. Other implications include pseudo-random number generation and number theory, which invariably is now somehow less theoretical. That concludes the talk. Thank you very much.